Dear friends, in today's episode, we are going to discuss D and F block elements. So, it's going to very interesting chapter. So, this chapter is brought to you by www.chemistrynotesinfo.com. Alternatively, you can also visit us at www.chemistrynotesinfo.blogspot.com. Introduction to D block elements. D block elements are elements as the elements from periodic table in which last electron enters into the d orbital of the penultimate cell, that is n minus 1 d orbital, where n is the last cell. D block elements are also called transition elements because their properties are intermediate between the properties of highly electropositive S block elements and highly electronegative P block elements. Transition elements have partially or incompletely filled n-1 d orbital in their elementary states. Transition elements are important elements in periodic table. Position of D block elements in periodic table. D block elements are placed between S block elements and P block elements. The elements are placed between group 3 to 12 belonging to the period 4 to 7. There are 4 series of transition elements, that is 3D, 4D, 5D and 6D series. The 3D series starts from scandium Z is equal to 21 to zinc Z is equal to 30 and belongs to 4th period. The 4D series includes all the elements from yttrium Z is equal to 39 to cadmium Z is equal to 48 and belongs to 5th period. The 5th series starts from the element lanthanum Z is equal to 57 and then includes all the elements from hafnium Z is equal to 72 to mercury Hg Z is equal to 80 and belongs to 6th period. Thus, 6D series starts from aconite Z is equal to 89 and then includes all the elements from raffinate Z is equal to 104 to UNB Z is equal to 112, which belongs to 7th period. Electronic configuration D block elements. General electronic configuration of 4 series of D block elements are given below. 3D series 3D 1 minus 10 4s 1 2. 4D series KR 4D 1 to 10 and 5s 0 to 2. 5D series XC 5D 1 to 10 6s 2. 6D RN 6D 1 to 10 and 7s 2. Abnormal electronic configuration of chromium and copper among D block elements. Chromium Cr has electronic configuration expected AR 3D4 4s2, observed AR 3D5 4s1. Copper Cu has electronic configuration expected AR 3D9 4s1, observed AR 3D10 4s1. Explanation: due to more stability of half filled and completely filled d orbital. Occurrence of D block elements. The soft elements of D block or transition elements occurs as sulfides minerals. Hard and electropositive elements occurs as oxides. General characteristics of D block elements. All the transition elements are metal having high melting as well as boiling point. They are good conductors of electricity and heat. They form complexes and colored compound. Due to unpaired electrons, most of the elements are paramagnetic, while some exhibit dimagnetic characters. They are good catalysts and they form alloys with different metals. General trend in properties of first row elements of d block. Ionization enthalpy. The ionization enthalpy of transition elements are quite high and lie between those of s block and p block elements. This is because the nuclear charge and atomic radii of transition elements lie between those of s and p block elements. If EI1, EI2 and EI3 are the first, second and third ionization enthalpies of transition elements, then IE1 is smaller than IE2 is smaller than IE3. The ionization enthalpies values of transition metal can be used to predict thermodynamic stability of their compound. Metallic characters. All the transition metals have high thermal as well as electrical conductivity and having very high melting and boiling points, compound to those of representative elements due to their closed packed structure. Ongoing across the period, melting point first increases, attain maximum value, then steadily decreases as atomic number. The strength of metallic bond depends upon the number of unpaired electrons. It increases up to middle, that is up to n-1 d5, hence accordingly melting and boiling points also increases. After n-1 d5 configuration, the electrons starts pairing, hence metallic strength and melting and boiling points decreases with increase in atomic number. Oxidation states. Transition metals exhibits variable oxidation states and form compounds showing more than one variable oxidation states because energies levels of Ns and n-1d are nearly similar. The oxidation state of 3D series is from +2 to +7 except chromium and copper. The lowest oxidation state of these elements are +1 or +2, which is due to their 4s electrons. As the number of unpaired electrons in 3D orbital increases, the number of oxidation states also increases from scandium to manganese, and after that electron starts pairing in 3D orbital, hence oxidation state decreases from iron to zinc. The highest oxidation state of transition element is +8, which shown by OS and RU. Atomic and ionic radii. Atomic radii of the elements of 3D series gradually decreases up to chromium and then remain almost same for a few more elements and then increases slightly towards the end of the series. In 3D series, the decrease in atomic radii is small from scandium to chromium because increase in nuclear charge at the center of atom and added electrons filled up in vacant ultimate d orbital. Atomic radii from chromium to copper are almost similar and then slightly increases to zinc. Ionic radii also follow similar trend as observed in atomic radii values. Color. Most of the compounds of transition metals are colored in their solid or solution form. Color of the compound of the transition metals may be attributed to the presence of the incomplete n-1d orbital and the number of unpaired electrons. Transition metal ions with no unpaired electrons are colorless because there is possibility of dd transition. Example: Sc +3 3d0, Ti +4 3d0, Cu plus 3d10. Ions with unpaired electrons are colored, that is, ions with electronic configuration 3d1 to 3d9 are colored. In general, The color of transition ions can be related to presence of unpaired d electrons, dd transition, nature of groups, that is ligands linked with two metal ions, geometry of the complexes formed by the metal ions. Catalytic properties. Many transition metals are used as catalysts which influence the rate of chemical reaction. A catalytic substance is capable of forming an unstable intermediate compound which readily decomposes, yielding the products and regenerating the catalyst. A plus B plus C gives ABC gives AB plus C. The commonly used transition metals as a catalyst are iron, cobalt, platinum, chromium, manganese, etc. Example: MnO2 act as a catalyst for decomposition of KClO3 to O2. In manufacture of ammonia, iron with molybdenum is used as catalyst. Nickel acts as catalyst in hydrogenation of oils to fats. Magnetic properties. Due to the presence of unpaired electrons in n-1d orbital, most of the transition metal ions and their compounds are paramagnetic, that is, they are attracted by magnetic field. The transition element and their ions having all electrons paired are dimagnetic, that is, they are repelled by magnetic field. Metals like iron, cobalt, nickel possesses very high paramagnetic and acquire permanent magnetic moment, hence they are ferromagnetic. Alnico is an alloy of aluminium 12%, nickel 20%, cobalt 50%, and remaining iron 18%. It is used to make permanent magnets. Bohr magnetron beam is unit of magnetic moment. 1 bm is equal to Eh divided by 4 pi mec. The effective magnetic moment mu effective of a paramagnetic substance is given by spin only formula. Mu effective is equal to root n in bracket n plus 2. Dear friends, you are learning this podcast with the help of chemistry notes, which is dictated by your friend Jitendra Singh Sandhu. Alloy formation. The transition metals can form large number of alloys among themselves having high melting point. In the molten state, transition metals are miscible with one another, which forms solid alloy on cooling. Transition metal can form alloy with non-transition metals such as brass, copper, zinc, and bronze, copper, and tin. Potassium dichromate, whose formula is K2Cr2O7. Properties of potassium dichromate. Potassium dichromate exits as orange-red crystals and is soluble in water. Action of alkali. Alkali KOH reacts with potassium dichromate to give yellow colored solution of potassium chromate. K2Cr2O7 plus 2KOH gives 2K2CrO4 plus H2O. Oxidizing properties. Potassium dichromate is good oxidizing agent in acidic medium. Potassium dichromate oxidation number of chromium is plus 6 is reduced to chromium sulfate. Oxidation number of chromium is plus 5 plus 3. So reaction is Cr2O7 2 minus plus 14H plus 6 electron gives 2Cr3 plus 7H2O. By gaining 6 electrons, dichromate ions act as an oxidizing agent. Structure of chromate ion and dichromate ion. Chromate ion has 4 oxygen atoms linked with chromium atom. and dichromate ion, in which three oxygen atoms linked with chromium, and then chromium linked with another oxygen atom, and which are also linked with another chromium atom, and which linked with another three oxygen atom. So dear friends, to view this structure you can visit our website www.chemistrynotesinfo.com or chemistrynotesinfo.blogspot.com, and under 12th class section you can find the chapter D and F block elements, where you can see the structure of this chromate ions and dichromate ion, and also read the complete notes from there, or you can also get the PDF notes of this chapter. Let's continue. Uses of potassium dichromate. It is used as an oxidizing agent, used in a dyeing, in manufacture of lead chromate and chromium alum, used in the detect ion of chloride ion, used in the detection of chloride ion, in the tanning of leather, in manufacturing of pigments and inks. Potassium permanganate KMnO4. Properties of potassium permanganate KMnO4. It is crystalline solid having deep purple color. It is soluble in water at room temperature. When heated, it decomposes, giving oxygen at 473 Kelvin. 2-KMnO4 gives K2MnO4 plus MnO2 plus O2. At red heat, it further decomposes to K2MnO3 plus oxygen. Heated solid KMnO4 gives KOH, MnO, and water vapors in current of H2. Uses of KMnO4. KMnO4 is used as disinfectant and oxidizing agent, Bayer's reagent for detecting halides in qualitative analysis. Now we are going to learn F block elements. Introduction of F block elements. The elements in which differentiating electrons, last electrons, enters into pre-penultimate cell, that is n-2 f orbital, are known as F block elements. F block elements are also known as inner transition elements. There are two series of inner transition elements: lanthanide series F block elements and actinoid series 5 F block elements. So lanthanide series is 4 F block elements, where actinoid series is 5 F block elements. Lanthanide series. This include all the elements from cerium Z is equal to 58 to lutetium Z is equal to 71, which are group of 14 elements with differentiating electron occupying 4f subcell. The name lanthanoid has been derived from lanthanum, which is prototype of lanthanoid. Lanthanoid series are also called 4f series because last electron enters pre-nultimate in 4f orbital. Position of lanthanoids. Lanthanoids belongs to group 3 of periodic table and are placed in the 6th period. Lanthanoids are shown at the bottom of periodic table because it interrupts third transition series of D block elements. Actual position of lanthanoids is in between Z is equal to 57 and hafnium Z is equal to 72. Electronic configuration of lanthanoids. The general electronic configuration of 4f block elements is Xe4f1214, 5d021 and 6s2. Elements La, Gd, Lu possess single electrons in 5d subcell. In case of other lanthanoids, 5d orbital is empty. Due to empty, half-filled and completely filled orbital, F0, F7 and F14 electronic configuration elements achieve extra stability. Oxidation states of lanthanoids. The common oxidation states of all lanthanoids is +3. It is characteristics of series lanthanum, gadolinium, lutetium shows only +3 oxidation states by losing two 6s and one 5d or electrons, giving stable outer electronic configuration 4f0, 4f7 and 4f14 respectively. In +4 oxidation state, cerium, terbium attains 4f0, 4f7 respectively. Europium as well as ytterbium attains 4f7, 4f14 respectively in +2 oxidation state. Chemical reactivity of lanthanoids. Earlier member of lanthanoids are quite reactive, behaves like calcium, but as atomic number increases they behave more like aluminium. Lanthanoids forms carbides, hydrides, oxides, nitrides, halides, etc. Carbides. Ln plus C gives lanthanoid carbide. Hydrides. 2Ln plus 3H2 gives 2LnH3. Oxides. 2Ln plus 3O2 gives 2Ln2O3. Nitrides. 2Ln plus N2 gives 2Ln. Halides. 2Ln plus 6HCl gives 2LnCl3 plus 3H2. Sulfides. 2Ln plus 3S gives Ln2S3. Lanthanoid contraction. The gradual decrease in atomic and ionic size of lanthanoids with increases in atomic number is called lanthanoid contraction. Dear friends, you can also visit our website Chemistry Notes Info to download PDF notes of this chapter. Alternatively, you can also join our Telegram channel, that is @Chemistry Notes Info, to download PDF notes. Causes of lanthanoid contraction. Increase in atomic number of members of lanthanoid series. The positive charge on nucleus increases by +1 unit and one more electron enters in the pre-nultimate 4f subcell. There is imperfect shielding of one electron by another electron in the same 4f subcell. With increase in nuclear charge, the valence shell is pulled slightly towards nucleus. As a result of the pull, the size of M plus 3 ions goes on decreasing with increase in atomic number. In complete lanthanoid series, atomic radii and ionic radii decreases with 10 picometer and 21 picometer respectively. Atomic radii shows some irregularities, but ionic radii decreases steadily. Effects of lanthanoid contraction. Decreases in basicity. Due to lanthanoid contraction, the size of the tripositive lanthanoid ion M plus 3 regularly decreases with increase in atomic number, that is from La plus 3 to La plus 3. It results into decrease of basicity from La plus 3 to Lu plus 3. Ionic radii of the post lanthanoids. The elements which follow the lanthanoids in the third transition series are known as post lanthanoids. As a result of lanthanoid contraction, the atomic radii size of the elements which follow lanthanum, HF, Ta, etc. are similar to that of the elements of 4D series, since ZR, HF, NBTA, MOW and TCRE have almost identical sizes. has similar number of valence electrons and similar properties. These pair of elements are called chemical twins. Actinoid series. The series of 14 elements TH90 to LR103, which follows actinium AC89 and in which last electrons are progressively filled in 5f orbital in pre-nultimate subset, are called actinoid series or 5f series. The elements which are synthetically or artificially prepared by man having atomic number higher than uranium Z is equal to 92 are called as transuranic elements Nb 93 to UNO 118. Position of actinoids. The actinoids belongs to third group of the periodic table in the seventh period. Actinoids are placed at the bottom of the periodic table below the lanthanoid series because it interrupts fourth transition series of d block elements. Electronic configuration. In general, electronic configuration of 5f elements is represented as 5f1 to 14, 6d0 to 1 and 7s2. The electronic configuration of actinoid is not defined. Actinium and thorium does not contains any 4f electron. Oxidation states of actinoids. Actinoids show varied oxidation states like lanthanoids. The common oxidation states of actinoid is +3 ACTH and AM shows +2 oxidation state THPAU NBPU AM and CM shows +4 oxidation states. +5 oxidation states is shown by elements TH2AM. U, NP, Pu and Am shows oxidation states +6. The higher oxidation state is +7 shown by Np and Pu. How to actually learn more about D and F block elements? Dear friends, in this podcast, you understand how to actually learn more about D and F block elements. You just completed learning of D and F block elements on our website or by listening this podcast. To learn more about chemistry, please visit our website www.chemistrynoteinfo.com and read content about chemistry there. Thank you for your great future. See you soon in our upcoming podcast. If you have any concern, please comment below our podcast. Thank you to listening this podcast. This podcast is brought to you by www.chemistrynoteinfo.com and this podcast is recorded by Jitendra Singh Sandhu. Jitendra Singh Sandhu is the host of this podcast.